Chapter 3, Functions. Toward the end of the 20th century, the values of stock markets and internet and technology companies rose dramatically. As a result, the Standard & Poor's stock market average rose as well. Figure 1 tracks the value of that initial investment of just under $100 over the 40 years. It shows that an investment that was worth less than $500 until about 1995 skyrocketed up to about $1,100 by the beginning of 2000. That 5-year period became known as the dot-com bubble because so many internet startups were formed. As bubbles tend to do, though the dot-com bubble eventually burst, many companies grew too fast and then suddenly went out of business. The result caused the sharp decline represented on the graph beginning at the end of 2000. Notice, as we consider this example, that there is a definite relationship between the year and stock market average. For any year we choose, we can determine the corresponding value of the stock market average. In this chapter, we will explore these kinds of relationships and their properties. 3.1 Functions and Function Notation. A jetliner changes altitude as its distance from the starting point of a flight increases. The weight of a growing child increases with time, and in each case, one quantity depends on another. There is a relationship between the two quantities that we can describe, analyze, and use to make the predictions. In this section, we will analyze such relationships, determining whether a relationship represents a function. A relationship is a set of ordered pairs, and the set consisting of the first components of each ordered pair is called the domain, and the set consisting of the second components of each ordered pair is called the range. Consider the following set of ordered pairs. The first numbers in each pair are the first 5 natural numbers. The second number in each pair is twice that of the first. And note that each value in the domain is also known as an input value or independent variable and is often labeled with the lowercase letter x. Each value in the range is also known as an output value or dependent variable and is often labeled lowercase letter y. A function f is a relation that assigns a single element in the range to each element in the domain. In other words, no x values are repeated. For our example, that relates the first 5 natural numbers to numbers double their values, this relation is a function because each element in the domain is paired with exactly one element in the range. Now, let's consider the set of ordered pairs that relates the terms even and odd to the first 5 natural numbers. Notice that each element in the domain, even, odd, is not paired with exactly one element in the range. For example, the term odd corresponds to 3 values from the domain, and the term even corresponds to 2 values from the range. This violates the definition of a function, so this relation is not a function. Figure 1 compares relations that are functions and not functions. Function. A function is a relation in which each possible input value leads to exactly one output value. We say the output is a function of the input. The input value makes up the domain and the output value makes up the range. How to? Given a relationship between 2 quantities, determine whether the relationship is a function. 1, identify the input values. 2, identify the output values. And 3, if each input value leads to only one output value, classify the relationship as a function. If any input value leads to 2 or more outputs, do not classify the relationship as a function. Using function notation. Once we determine that a relationship is a function, we need to display and define the functional relationships so that we can understand and use them, and sometimes also so that we can program them into graphing calculators and computers. There are various ways of representing functions. A standard function notation is one representation that facilitates working with functions. To represent height is a function of age. We start by identifying the descriptive variables h for height and a for age. The letters f, g, and h are often used to represent functions as we use x, y, and z to represent numbers, a, b, and c to represent sets. H is f of a, and we name the function f. Height is a function of age. h equals f of a, we use parentheses to indicate the function input, and f of a, we name the function f. The expression is read as f of a. Remember, we can use any letter to name the function. The notation h of a shows us that h depends on a. The value a must be put into the function h to get a result. The parentheses indicate that h is input into the function. They do not indicate multiplication. We can also give an algebraic expression as the input to a function. For example, f of a plus b means first add a and b, and the result is the input for the function f. The operations must be performed in this order to obtain the correct result. Function notation. The notation y equals f of x defines a function named f. This is read as y is a function of x. The letter x represents the input value or dependent variable, and the letter y or f of x represents the output value or dependent variable. Q&A. Instead of a notation such as y equals f of x, could we use the same symbol for the output as for the function, such as y equals y of x, meaning y is a function of x? Well, yes, this is often done, especially in applied subjects that use higher math, such as physics and engineering. However, in exploring math itself, we like to maintain a distinction between a function such as f, which is a rule or procedure, and the output y we get by applying f to a particular input x. This is why we usually use notation such as y equals f of x and p equals w of d, and so on. Representing functions using tables. A common method of representing functions is in the form of a table. The table rows or columns display the corresponding input and output values. In some cases, these values represent all we know about the relationship. Other times, the table provides a few select examples from a more complete relationship. Table 3 lists the input number of each month, January equals 1, February equals 2, and so on, and the output value of the number of days in that month. This information represents all we know about the months and days for a given year that is not a leap year. And note that in this table, we define a days in month function, f, where d equals f of m, identifies months by an integer rather than by a name. Table 4 defines a function q equals g of n, and remember this notation tells us that g is the name of the function that takes the input n and gives the output q. Table 5 below displays the age of children in years and their corresponding heights. This table displays just some of the data available for the heights and ages of children. And we can see right away that this table does not represent a function because the same input value, 5 years, has two different output values, 40 inches and 42 inches. How to? Given a table of input and output values, determine whether the table represents a function. 1. Identify the input and output values, and 2. Check to see if each input value is paired with only one output value. If so, the table represents a function. Finding input and output values of a function. When we know an input value and want to determine the corresponding output value for a function, we evaluate the function. Evaluating will always produce one result because each input value of a function corresponds to exactly one output value. When we know an output value and want to determine the input values that would produce that output value, we set the output equal to the function's formula and solve for the input. Solving can produce more than one solution because different input values can produce the same output value. Evaluation of functions in algebraic forms. When we have a function in formula form, it is usually a simple matter to evaluate the function. For example, the function f of x equals 5 minus 3x squared can be evaluated by squaring the input value, multiplying by 3, and then subtracting the product from 5. How to? Given the formula for a function, evaluate. 1. Replace the input variable in the formula with the value provided. 2. Calculate the result. Evaluating functions expressed in formulas. Some functions are defined by mathematical rules or procedures expressed in equation form. If it is possible to express the function output with a formula involving the input quantity, then we can define a function in algebraic form. For example, the equation 2n plus 6p equals 12 expresses a functional relationship between n and p, and we can rewrite it to decide if p is a function of n. How to. Given a function in equation form, write its algebraic formula. 1. Solve the equation to isolate the output variable on one side of the equal sign, with the other side as an expression that involves only the input variable. 2. Use all the usual algebraic methods for solving equations, such as adding or subtracting the same quantity to or from both sides, or multiplying or dividing both sides of the equation by the same quantity. Q&A. Are there relationships expressed by an equation that do represent a function, but that still cannot be represented by an algebraic formula? Yes, this can happen. For example, given the equation x equals y plus 2 raised to the y power, if we want to express y as a function of x, there is no simple algebraic formula involving only x that equals y. However, each x does determine a unique value for y, and there are mathematical procedures by which y can be found to any desired accuracy. In this case, we say that the equation gives an implicit, implied rule for y as a function of x, even though the formula cannot be written explicitly. Evaluating a function given in tabular form. As we saw above, we can represent functions in tables. Conversely, we can use information in tables to write functions, and we can evaluate functions using the tables. For example, how well do our pets recall the fond memories we share with them? There is an urban legend that a goldfish has a memory of 3 seconds, but this is just a myth. Goldfish can remember up to 3 months, while the betta fish has a memory for up to 5 months. And while a puppy's memory span is no longer than 30 seconds, the adult dog can remember for 5 minutes. This is meager compared to a cat whose memory span lasts for 16 hours. So the function that relates the type of a pet to the duration of its memory span is more easily visualized with the use of tables seen in Table 10. At times, evaluating a function in table form may be more useful than using equations. So here, let us call the function p. The domain of the function is the type of pet, and the range is a real number representing the number of hours the pet's memory span lasts. And we can evaluate the function p at the input value of goldfish. We would write p of goldfish equals 2,160. Notice that to evaluate the function in table form, we identify the input value and the corresponding output value from the pertinent row of the table. The tabular form for the function p seems ideally suited to this function, and more so than writing it in paragraph or function form. How to. Given a function represented by a table, identify specific output and input values. 1. Find the given input in the row or column of input values. 2. Identify the corresponding output value paired with that of the input value. 3. Find the given output values in the row or column of output values, noting every time that output value appears. And 4. Identify the input values corresponding to the given output value. Finding function values from a graph. Evaluating a function using a graph also requires finding the corresponding output value for a given input value, and only in this case, we find the output value by looking at the graph. Solving a function equation using a graph requires finding all instances of the given output value on the graph and observing the corresponding input values. Determining whether a function is one-to-one. Some functions have a given output value that corresponds to 2 or more input values, and for example, in the stock, chart shown in figure 1, at the beginning of this chapter, the stock price was $1,000 on 5 different dates, meaning that there were 5 different input values that all resulted in the same output values of $1,000. However, some functions have only one input value for each output value, as well as having only one output value for each input. We call these functions one-to-one functions. So as an example, consider a school that uses only letter grades and decimal equivalents, as listed in Table 12. This grading system represents a one-to-one function because each letter input yields one particular grade point average output, and each grade point average corresponds to one input letter. To visualize this concept, let's look again at the 2 simple functions sketched in Figure 1a and Figure 1b. The function in part A shows a relationship that is not a one-to-one function because inputs Q and R both give output function N. The function in part B shows a relationship that is one-to-one function because each input is associated with a single output. One-to-one function. A one-to-one function is a function in which each output value corresponds to exactly one input value, and there are no repeated X or Y values. Using the vertical line test. As we have seen in some examples above, we can represent a function using a graph. Graphs display a great many input-output pairs in a small space, and the visual information they provide often makes relationships easier to understand. By convention, graphs are typically constructed with the input values along the horizontal axis and the output values along the vertical axis. The most common graphs name the input value x and the output value y, and we say it is a function of x or y equals f of x. When the function is named f, the graph of the function is the set of all points x, y in the plane that satisfies the equation y equals f of x. If the function is defined for only a few input values, then the graph of the function consists of only a few points where the x-coordinate of each point is an input value and the y-coordinate of each point is the corresponding output value. For example, the black dots on the graph in figure 9 tell us that f of 0 equal 2 and f of 6 equal 1. However, the set of all points x and y satisfying y equals f of x is a curve. The curve shown includes 0, 2, and 6, 1 because the curve passes through these points. The vertical line test can be used to determine whether a graph represents a function. If we can draw any vertical line that intersects a graph more than once, then the graph does not define a function because a function has only one output value for each input value. How to? Given a graph, use the vertical line test to determine if the graph represents a function. 1. Inspect the graph to see if any vertical line drawn would intersect the curve more than once. And 2. If there is any such line, determine that the graph does not represent a function. Using the horizontal line test. Once we have determined that a graph defines a function, an easy way to determine if it is a one-to-one function is to use the horizontal line test. Draw horizontal lines through the graph. If any horizontal line intersects the graph more than once, then the graph does not represent a one-to-one function. So how to? Given a graph of a function, use the horizontal line test to determine if the graph represents a one-to-one function. 1. Inspect the graph to see if any of the horizontal line drawn would intersect the curve more than once. And 2. If there is any such line, determine that the function is not one-to-one. Identifying basic toolkit functions. In this text, we will be exploring functions, the shapes of their graphs, their unique characteristics, their algebraic formulas, and how to solve problems with them. When learning to read, we start with the alphabet. When learning to do arithmetic, we start with numbers. And when working with functions, it is similarly helpful to have a base set of building block elements. We call these our toolkit functions, which form a set of basic named functions for which we know the graph, formula, and special properties. Some of these functions are programmed to individual buttons on many calculators, and for these definitions, we will use x as the input variable and y equals f of x as the output variable. We will see these toolkit functions, combinations, and toolkit functions, their graphs, and their transformations frequently throughout this book. It will be very helpful if we can recognize these toolkit functions and their features quickly by name, formula, graph, and basic table properties. The graphs and sample table values are included with each function shown in Table 13 on page 174. Access the following online resources for additional instruction and practice with functions: openstackscollege.org.